Good afternoon, everyone. Thank you for being here. Today, I'm presenting our paper by Coppola for analyzing multivariate conditional dependence in electronic health records data. And we would also like to express our gratitude to the U.S. National Science Foundation for supporting this work. To start with the problem part, on the clinical side, there are hundreds of demographic and laboratory variables in the electronic medical records data. Also, the data is inherently mixed type. It combines continuous lab panels, discrete diagnosis code, and ordinal metrics. Because these health metrics are deeply interconnected, they show highly complex nonlinear conditional relationships. Most importantly, they suffer from severe tail dependence, meaning extreme medical events or abnormal values often happen together. Also, on the technical side, traditional methods rely on oversimplified assumption. They assume normally distributed data, variable independence, and simple linear association, which are not perfectly matched with the data situation. Our motivation comes from directly addressing this EHR data challenge using one Copulas solution. First, regarding non-Gaussian distribution, EHR data rarely follows a abnormal bell curve. However, one Coppola are entirely data adaptive, extract the best fit distribution directly from the data. Second, instead of struggling with mixed type variables like continuous lab value and discrete codes, our framework offers native integration by standardizing everything into a unified scale. Third, where traditional learning methods means nonlinear and tail association, pair Coppola isolate this complex interaction and structure the tail links. Finally, to prevent high-dimensional scaling from dropping crucial conditional context, we use hierarchical representation to break a massive space down into a simple two variable trees. Therefore, we leverage a one cupola method to model conditional independence in high dimensional EHR data in our study. Let's see a review of how we extract and curate real-world EH data from all of us research program, which is one of the largest biomedical data source, including EHR domain, survey responses, and physical measurements. First, we select heart failure and patients who doesn't have cardiovascular diseases based on ICD-10 code. Second, according to other heart failure research and variable missing rate, we select 33 medical features along with gender from out of more than 200 medical measurements. Third, we keep medical records whose data is closest to the disease diagnosis date, and also we keep the same unit for each medical features and clean the outlier. Finally, we get two cohort for heart failure cohort. It has more than 6,000 samples. For non-cardiovascular groups, it has more than 16,000 samples. Both of them have 34 variables, and their missing rate are lower than 1%. We also created another dataset for comorbidity study. We select the patients who has at least one ICD-10 code and got the top 20 frequency comorbidities along with age, sex, and BMI to be the features. This dataset has more than 0.2 million patients without any missingness. Now let's look at the mathematical foundation of our couple of how a cupola actually works. Let's begin with a random vector x, where each clinical variable has its own marginal cumulative distribution function, which is F here according to the Ziegler's theorem. We can factorize any multivariate joint distribution F into a unique d-dimension cupula. This cupula completely captures the true underlying dependency structure between our variables. When we look at the joint density factorization, it shows that the overall joint density is simply the product of these individual margin densities multiplied by cupula densities. Instead of trying to evaluate the d-dimensional cupula as one massive block, we factorize it into a clean product of a pair cupula across d minus 1 tree levels. As shown in this example diagram, tree 1 captures the direct relationship between two variables, while tree 2 captures the next relationship conditioned on that central variable. There are three ways we can structure this one trees. First, the D1 tree is a sequential chain structure. It's best for time series or ordered data. Second, the C1 is a star-shaped. One central node conditions all others. We use this structure specifically when we want to identify the single most influential variables in the dataset. Finally, the R1 is a hybrid of C and C1 and D1. It's most flexible because it reveals multiple central variables and local cluster without forcing a specific shape. In this study, we focus on C1 and R1 trees to interpret medical conditions. So why we are using R1 tree? Because as shown in the figure, the first tree level excels at capturing feature dependence between nearby variables. This make it perfect for identifying local cluster of variables and analyzing comorbidity pathways. And why we are using C1 trees? Because for each tree center, it allows us to capture conditional independence in one versus all fashion. This lets us to determine the most influential variables at that layer. The D1 in the following d minus 1 trees give us as the exact order of variable based on the conditional dependence of other variables, which allow us to select clinical variables. Let's dive into our results, starting with the C-vine analysis on our combined dataset, which includes both heart failure and non-cardiovascular patients. As shown in the figure, sex is a root central node in tree 1. It means all other variables conditionally depend on it. Proving that sex is the most impactful variable determines the baseline values of all other clinical metrics. When we look at the center of subsequent D minus 1 trees, hemoglobin appears as a central node for tree 2, followed by MCH in tree 3, and the heart failure diagnosis code is in the tree 4. Next, we split our data into separate gender and diagnosis cohorts, looking at the first two columns in the diagram, both male, female heart failure patients. There is a consistent pattern in these first four trees. So hemoglobin, MCH, local leukocyte and the age are central for the first four trees. This aligns perfectly with established medical literature. Low hemoglobin is observed up to 70% of heart failure patients, and reduced MCH is a well-documented independent predictor of heart failure mortality, while higher leukocyte act as an inflammatory marker predictive of diverse outcomes. In contrast, the non-cardiovascular cohort shows a completely inconsistent pattern, where clinical variables depend primarily on the same, but they're in a different order. Now we will focus on the C1 trains. Uh, the first global R1 train from the combined, still for the combined cohort. The first subfigure shows that creatinine, height, and ALT conditionally depend on patient's sex. In the second subfigure, maps the variables centered on age, showing that heart rate, blood pressure, and urine nitrogen are all depend directly on age. In the third figure, heart failure diagnosis code conditionally links to respiratory rate, leukocyte, glucose, and ALP. This cluster highlights the exact clinical variables that natively stratify our two patient cohorts. In the first figure, hematocrit and protein related directly to calcium, matching the clinical fact that plasma protein is the main binding substance of calcium. In the last figure, shows that hemoglobin is directly linked to hematocrit and your three-side distribution-wise, which makes sense since red blood cells are filled with hemoglobin. We also applied our R1 framework to comorbidity dataset. Cluster A is centered on pain, which naturally binds together with four other conditional with four other conditions. Cluster B is centered on overweight and obesity, linking it directly to BMI, type 2 diabetes, and sleep disorder. This minors the clinical reality that over 90% of individuals with type 2 diabetes are overweight. Cluster C shows that throat and chest pain are conditionally linked to heartbeat abnormal and breathing issues. The next clusters clusters breathing abnormal tightly with cough, throat pain, sleep disorder, and fatigue. Finally, cluster E positions sleep disorder as a central hub connecting breath problem, obesity, acid reflux, and depressive episodes, capturing the well-known bidirectional risks between these conditions. So all these clusters align with established clinical literature. To conclude, our work successfully demonstrate a variable shift for wine copulas to using them as a powerful interpretable tool for clean healthcare data mining. Through C1 trains, we isolate global clinical relationships, proving that sex acts a central root condition that fundamentally shape downstream lab measurement and physical distributions. Through R1 trains, our model automatically clustered complex interconnected diseases and comorbidity pathway purely from data patterns. All of them are firmly verified by established medical literature. For the future work, we plan to benchmark our framework against other baselines, such as different graph models and sparse precision matrix estimation. We want to apply this methodology to additional diseases cohort beyond heart failure. Finally, we aim to explore using this discovered the wine cupola structure as structure input features for downstream predictive machine learning models to improve patient stratification. Here are the references used in this presentation. That's all for my presentation. Thank you for listening. Please ask me any questions.